Have you ever looked up at the night sky and wondered what it would be like to simply walk to another world? Tonight, we're going to explore one of the most wonderfully impossible journeys imaginable. We'll calculate exactly how long it would take to walk to every planet in our solar system, step by gentle step, using nothing more than the steady rhythm of human feet. Before we begin this cosmic stroll, take a moment to settle in. Maybe dim the lights, adjust your pillow, and let your breathing find its natural pace. We're about to embark on a journey that will stretch across unimaginable distances and timescales that dwarf human experience. Yet somehow, by breaking it down into the simple act of walking, we can make the vastness of space feel just a little more approachable. Now, let's start with the basics. The average human walking speed is remarkably consistent across cultures and continents. Most of us naturally walk at about 3 to 4 miles per hour, which translates to roughly 5 kilometers per hour. This is the pace of a leisurely stroll through a park, unhurried and comfortable. It's the speed at which our ancestors crossed continents and explored new lands. For our calculations tonight, we'll use this gentle, sustainable pace of 5 kilometers per hour. Of course, walking to another planet presents some immediate challenges that we need to address with calm, scientific honesty. Space, as we know it, is a vacuum. There's no air to breathe, no ground to walk on, and no protection from the extreme temperatures and radiation that fill the void between worlds. In reality, a human exposed to the vacuum of space would lose consciousness within 10 to 15 seconds and would not survive more than a minute or two. But let's imagine, for the sake of our peaceful thought experiment, that we could somehow create a path through space, perhaps a narrow bridge of breathable atmosphere stretching like a cosmic sidewalk between the planets. We'll need to suspend certain laws of physics for this journey to even begin, but we'll do so gently, acknowledging that this is purely a mathematical meditation on distance and time. With our imaginary cosmic pathway established, let's begin our walk. But where shall we start? The most logical first destination is our closest celestial neighbour, the Moon. At an average distance of 384,400 kilometres from Earth, the Moon represents humanity's first tentative step into the cosmic ocean. Walking to the Moon at our steady pace of 5 kilometers per hour would take us approximately 76,880 hours. That's about 8.8 years of continuous walking, never stopping for rest, food, or sleep. Imagine setting out on this journey as a young adult and arriving as someone approaching middle age, having spent nearly a decade placing one foot in front of the other across the silent void. But the Moon, close as it seems in our night sky, is merely the beginning. To reach the true planets of our solar system, we must venture far beyond this familiar companion. Let's continue our walk toward Mercury, the smallest planet and the one closest to our Sun. Mercury's distance from Earth varies dramatically as both planets follow their elliptical orbits around the Sun. When Mercury and Earth are at their closest approach, they're separated by approximately 77 million kilometers. At their farthest, this distance stretches to about 222 million kilometers. For our calculation, let's use the closest approach distance, giving our cosmic walker the best possible chance. Walking 77 million kilometers at 5 kilometers per hour would require 15.4 million hours. That's approximately 1,760 years of non-stop walking. Think about that for a moment. If you had started this journey during the time of the Roman Empire, you would only now be arriving at Mercury. Entire civilizations would have risen and fallen during your walk. Languages would have evolved, continents would have shifted slightly, and thousands of generations would have been born and lived their entire lives, while you maintained your steady pace through the darkness. The very idea stretches our understanding of time. We're accustomed to measuring our lives in decades, perhaps thinking ahead 1 or 2 generations. But a walk to Mercury spans nearly 2 millennia, a time frame that encompasses the entire recorded history of many cultures. And Mercury is just the beginning. Venus, often called Earth's twin due to its similar size, presents an even greater challenge. Venus orbits closer to the Sun than Earth, and at its nearest approach, it comes within about 41 million kilometers of our planet. This might seem closer than Mercury's maximum distance, but Venus's average distance from Earth is still formidable. Walking to Venus would require approximately 8.2 million hours, or about 940 years of continuous movement. This is still an almost incomprehensible span of time. If you had begun walking to Venus during the construction of the great cathedrals of medieval Europe, you would be arriving just as humanity ventures into space. But here's where our journey begins to reveal something profound about the architecture of our solar system. As we move outward from the Sun, the distances don't just increase, they expand exponentially. Mars, the red planet that has captured human imagination for centuries, sits at an average distance of about 78 million kilometers from Earth. At its closest approach, Mars comes within approximately 55 million kilometers of our world. Using the closest approach distance, a walk to Mars would take about 11 million hours, roughly 1,260 years. Once again, we're looking at a journey that spans more than a millennium. You could have started walking to Mars during the Viking explorations of North America, and would only now be taking your first steps on the rusty, iron-rich soil of the red planet. These inner planets, Mercury, Venus, and Mars, are often called the terrestrial planets because they have solid surfaces where our imaginary walker could theoretically set foot. But as we prepare to venture beyond Mars, we encounter something fundamentally different in the structure of our solar system. Between Mars and Jupiter lies the asteroid belt, a region filled with rocky debris left over from the formation of our solar system. Beyond this cosmic rubble field, we enter the realm of the gas giants, massive planets that dwarf the inner worlds in both size and the distances that separate them from Earth. Jupiter, the king of planets, is so large that it could contain all the other planets in our solar system with room to spare. But it's Jupiter's distance from Earth that truly begins to reveal the vast emptiness of space. At its closest approach, Jupiter is approximately 588 million kilometers from Earth. At its farthest, this distance stretches to nearly 968 million kilometers. Walking to Jupiter at its closest approach would require an almost unimaginable 117.6 million hours. That's approximately 13,420 years of continuous walking. Let's pause and really absorb this number. If you had started walking to Jupiter at the end of the last ice age, when humans were just beginning to develop agriculture, you would only now be arriving at this massive world. Think about everything that has happened in human history during that time frame. The rise and fall of countless civilizations, the development of writing, mathematics, philosophy, art, and science. The entire span of recorded human history would fit comfortably within your walking journey to Jupiter, with thousands of years to spare. And Jupiter, massive as it is not even the most distant planet we can see with the naked eye. Saturn, with its magnificent rings, orbits even farther from the Sun. At its closest approach to Earth, Saturn is approximately 1.2 billion kilometers away. Walking this distance would take about 240 million hours, or roughly 27,400 years. To put this in perspective, if you had started walking to Saturn when the first modern humans were creating cave paintings in Europe, you would still have thousands of years left in your journey. Your walk would span the entire development of human civilization, from the earliest agricultural settlements to the space age and far beyond. As we contemplate these vast distances, something interesting happens to our perception of time itself. When we talk about walking for thousands or tens of thousands of years, we begin to move beyond human timescales entirely. We enter what astronomers call geological time, the slow rhythm by which planets form, mountains rise and fall, and species evolve. The outer planets of our solar system exist in this realm of geological time. Uranus, the tilted ice giant, sits at an average distance of about 2.87 billion kilometers from Earth. Walking to Uranus would require approximately 574 million hours, or about 65,500 years. This is a time frame that encompasses the entire evolution of modern humans as a species. And finally, there's Neptune, the windiest planet in our solar system, with storms that rage at speeds of up to 2,100 kilometers per hour. Neptune orbits at an average distance of about 4.5 billion kilometers from Earth. Walking to Neptune would take approximately 900 million hours, or roughly 102,700 years. This is a journey that would span multiple ice ages. If you had started walking to Neptune when our ancestors first began using tools, you would still be walking today, with tens of thousands of years remaining in your journey. As these numbers wash over us, we begin to understand something fundamental about our place in the cosmos. The universe operates on scales that dwarf human experience. The distances between worlds are so vast that even light, the fastest thing in the universe, takes hours to travel between the outer planets. Yet there's something oddly comforting about breaking these cosmic distances down into the simple act of walking. By imagining ourselves taking step after step across the void, we make the infinite feel finite, the incomprehensible feel somehow manageable. Each step becomes a unit of measurement, each hour a milestone on an impossible journey. The rhythm of walking is deeply embedded in human nature. It's how our ancestors explored every continent on Earth, how they crossed mountains and deserts and frozen wastelands. Walking is patient, persistent, and inherently hopeful. It assumes that any distance, no matter how great, can eventually be covered if you just keep putting one foot in front of the other. In our cosmic walk, we've discovered that the solar system is far more empty than full, far more space than matter. The planets, despite their impressive sizes, are tiny islands in an ocean of nothingness. Even our own Earth, which feels so solid and substantial beneath our feet, is just a small blue dot suspended in the vast darkness. In the vast darkness. But this vastness isn't empty in the way we might imagine. Between the planets, space itself tells a story of incredible hostility and beauty. The void that separates worlds isn't just an absence of air and matter. It's filled with radiation from our sun, charged particles streaming outward in what we call the solar wind, and the background hum of cosmic rays from distant stars. If our imaginary walker could somehow maintain their steady pace through this environment, they would encounter temperatures that swing between extremes we can barely fathom. In the sunlight, without an atmosphere to moderate the heat, surfaces can reach hundreds of degrees. In shadow, temperatures plummet to nearly absolute zero, where even the motion of atoms slows to almost nothing. The radiation alone would be lethal within minutes. Our Earth's magnetic field and atmosphere work together like an invisible shield, deflecting most of the harmful particles that stream constantly from the sun. But step outside this protective bubble, and you're exposed to an environment that would damage every cell in your body almost immediately. Yet, in our gentle thought experiment, we continue walking. And as we do, we begin to notice something remarkable about the rhythm of our cosmic journey. The planets don't simply get farther apart as we move outward. The gaps between them grow exponentially, following what astronomers call the Tychus-Bode law, a mathematical pattern that roughly describes planetary spacing. This means that while the walk from Earth to Mars might take a little over 1,000 years, the journey from Mars to Jupiter requires more than 10 times as long. And the gap from Jupiter to Saturn is larger still. We're not just walking through space anymore, we're walking through time itself, each step carrying us deeper into a realm where human intuition about distance and duration begins to break down completely. Consider the asteroid belt that lies between Mars and Jupiter. This region, often depicted in movies as a dense field of tumbling rocks, is actually mostly empty space. The asteroids are spread so far apart that if you stood on one, you might not even be able to see the next closest one with the naked eye. Our walker could spend decades crossing this region and encounter nothing but emptiness, punctuated by the occasional glimpse of a distant, slowly tumbling rock. The belt itself would take roughly 150 years to cross, even at its narrowest point. This is longer than most nations have existed, longer than any human institution has endured unchanged. You could begin crossing the asteroid belt in one historical era and emerge in another, having walked through a century and a half of human progress and change while barely making a dent in your journey to the outer planets. As we finally emerge from the asteroid belt and approach Jupiter, the scale of what we encounter defies our earthbound experience. Jupiter is so massive that its gravitational field begins to affect our walker while they're still millions of kilometers away. The planet contains more matter than all the other planets combined. It's so large that Earth could fit inside it more than 1,300 times. But Jupiter has no surface in the traditional sense. It's a gas giant, composed mostly of hydrogen and helium under tremendous pressure. As our walker descended through Jupiter's thick atmosphere, the pressure would increase gradually until the gas became liquid, then eventually a metallic form of hydrogen that doesn't exist naturally on Earth. There would be no solid ground to stand on, just layers of increasingly dense matter extending down toward a rocky core that may or may not exist. The walk to Jupiter's cloud tops represents more than just a journey through space. It's a passage through deep time, the kind of duration that geologists use to measure the formation of mountains and the evolution of species. If you had started this walk when the first humans developed language, you would arrive at Jupiter speaking words that no longer exist, carrying cultural memories that had been forgotten for millennia. And yet, Jupiter is only halfway to the edge of our solar system's planetary realm. Beyond it lies Saturn, the ringed jewel of our cosmic neighborhood. Saturn sits nearly twice as far from the Sun as Jupiter, at an average distance of about 1.4 billion kilometers from Earth. The walk to Saturn would require approximately 28,000 years of continuous movement. This is a time frame that spans the entire development of human civilization. When the last ice age ended, and humans began settling into permanent communities, developing agriculture, building the first cities, creating writing systems, and establishing the foundations of all our modern knowledge, they could have started walking to Saturn. That journey would only now be reaching its destination. Saturn itself presents a puzzle wrapped in beauty. Its magnificent ring system, visible through even a small telescope, consists of countless particles of ice and rock, each following its own precise orbit around the planet. These rings are incredibly thin relative to their diameter, sometimes only a few hundred meters thick, despite stretching across hundreds of thousands of kilometers. The rings tell us something profound about the nature of celestial mechanics. Each tiny particle follows the same laws of physics that govern the planets themselves. They orbit Saturn in perfect harmony, held in place by a delicate balance of gravitational forces that have persisted for millions of years. Our walker, approaching Saturn after nearly 300 centuries of travel, would witness one of the most elegant demonstrations of cosmic order in our solar system. But as we continue our journey beyond Saturn, we enter a realm where even these vast distances begin to seem modest. The outer planets, Uranus and Neptune, exist in a region of space so remote that sunlight takes hours to reach them. At these distances, our sun appears as little more than a bright star, offering virtually no warmth to these frozen worlds. Uranus, the tilted ice giant, rolls along its orbit like a cosmic bowling ball, its axis of rotation nearly perpendicular to its orbital plane. The walk to Uranus would take approximately 65,000 years, a time frame that encompasses the entire history of modern human behavior. When our species first began creating art, music, and complex tools, we could have started walking to Uranus. That journey would still be continuing today, with thousands of years remaining. The distance to Uranus is so great that radio signals from Earth take nearly 3 hours to reach the planet. This means that any conversation between Earth and a hypothetical visitor to Uranus would involve delays longer than most movies. The simple act of communication across these distances challenges our understanding of connection and immediacy. And finally, there is Neptune, the windy blue giant at the edge of our planetary system. Neptune orbits at such a vast distance from the Sun that it takes 165 Earth years to complete a single orbit. Since its discovery in 1846, Neptune has only recently completed its first full orbit around the Sun, as observed by human eyes. The walk to Neptune would require more than 100,000 years, a duration that dwarfs the entire span of human civilization. This is deep time, the rhythm of geological change and biological evolution. If our earliest ancestors had started walking to Neptune when they first discovered fire, they would still be walking today, having passed the knowledge and purpose of their journey down through thousands of generations. At Neptune's distance, our Sun provides 1,000 times less light than we receive on Earth. High noon on Neptune would feel like deep twilight on our world. The planet experiences some of the most violent weather in the solar system, with winds reaching speeds of up to 2,100 kilometers per hour, despite receiving virtually no energy from the Sun to drive these storms. The existence of such powerful winds on such a cold, distant world remains one of the mysteries of planetary science. Neptune challenges our understanding of how planetary atmospheres work, reminding us that even after centuries of observation, the universe continues to surprise us with phenomena we don't fully comprehend. As our cosmic walk reaches its conclusion at Neptune's orbit, we've traveled approximately 4.5 billion kilometers from Earth. This journey has taken us more than 100,000 years of continuous walking, a time frame that spans the entire development of human consciousness, language, culture, and technology. But perhaps the most remarkable aspect of this impossible journey isn't the distance or the time. It's what the journey reveals about the nature of space itself. The universe is not crowded with matter. It's almost entirely empty, with tiny islands of substance separated by oceans of nothingness that challenge human comprehension. Each planet we visited on our walk represents a unique world with its own weather patterns, geological processes, and chemical compositions. Yet, all of these worlds combined would fit comfortably within the orbit of our own moon. The vast majority of space contains nothing at all, just the quantum fluctuations of empty vacuum and the occasional wandering particle. This emptiness isn't a flaw in the universe's design. It's fundamental to how cosmic structures form and evolve. Without these vast distances, planetary orbits wouldn't be stable. Without the emptiness between stars, light from distant galaxies couldn't reach us. The universe's spaciousness is what allows complexity and beauty to emerge over cosmic time. Our walking journey has taken us through this spaciousness step by step, making the infinite feel manageable through the simple human act of placing one foot in front of the other. In doing so, we've discovered something profound about both the universe and ourselves. The cosmos operates on scales that dwarf human experience, yet we can understand these scales through patience, imagination, and the quiet persistence of walking. Each step becomes a meditation on distance and time, each milestone a reminder that the universe, vast as it is, can be explored and comprehended by curious minds willing to take the journey slowly and thoughtfully. In the end, our walk to the planets teaches us that we are both infinitesimally small and remarkably significant. Small because we exist on a tiny world in a vast universe. Significant because we alone among Earth's creatures can contemplate these distances, calculate these journeys, and find meaning in the cosmic emptiness that surrounds us, uns us. The scale of these journeys transforms our understanding of what distance truly means. When we measure our daily walks in steps, perhaps a few thousand to reach the corner store, or several miles through a favorite park, we operate within a framework that feels natural and manageable. But as our cosmic footsteps carry us deeper into the solar system, we enter realms where human intuition about space and time begins to dissolve into something far more mysterious. Walking has always been humanity's most fundamental form of exploration. For hundreds of thousands of years, our ancestors crossed continents at roughly this same gentle pace we've been using in our calculations. They walked from Africa to Asia, across the Bering Land Bridge to the Americas, and eventually to every habitable corner of our planet. The farthest any human has ever walked in a single journey spans perhaps 20,000 miles, crossing multiple continents over several years. Yet even this most ambitious terrestrial walk represents less than 1/10,000th of the distance to our nearest planetary neighbour. The gap between human achievement and cosmic reality is so vast that it challenges our ability to process these numbers meaningfully. We can calculate the mathematics, but truly comprehending what a million-year walk means requires a different kind of thinking altogether. Consider how memory works across these timescales. A journey to Neptune lasting over 100,000 years would span more than 3,000 human generations. If each generation could somehow pass down the purpose and direction of this cosmic pilgrimage, the story would be retold more times than all the folktales, myths, and histories that have ever been preserved by human civilization. The walkers who arrived at Neptune would be so genetically different from those who began the journey that they might constitute an entirely new species. Evolution itself operates on timescales shorter than our longest planetary walks. The humans who finally set foot on Neptune's hypothetical surface would have adapted to their cosmic environment over tens of thousands of generations, becoming something we can barely imagine. But perhaps the most profound aspect of these calculations isn't the distance or time involved. It's what they reveal about the nature of space itself. The universe doesn't just happen to be mostly empty. This emptiness is fundamental to its structure and evolution. Without these vast gaps between celestial bodies, the gravitational interactions that create stable orbits couldn't exist. Imagine if the planets were packed together like marbles in a jar. The gravitational chaos would be immediate and catastrophic. Worlds would careen into each other, their orbits destabilized by constant interference from nearby neighbors. The delicate dance of planetary motion that has persisted for billions of years depends entirely on these enormous stretches of nothingness that separate each world. This emptiness also means that space is incredibly quiet. Sound requires matter to travel through, molecules of air or water or solid material that can vibrate and carry acoustic waves. In the vacuum between planets, there are so few particles per cubic meter that sound simply cannot exist. Our cosmic walker would travel in absolute silence, broken only by the gentle rhythm of their own heartbeat and breathing within whatever impossible life support system makes this journey conceivable. The silence of space is profound in ways that earthbound experience cannot prepare us for. On our planet, we're surrounded by the constant whisper of moving air, the distant hum of geological processes, the faint sounds of life in all its forms. Even in the quietest places on Earth, sensitive instruments can detect the subtle vibrations of wind, water, and living things. But in space, silence is complete. It's not the absence of sound we might experience in a soundproof room. It's the absence of the very medium through which sound travels. This creates a kind of sensory isolation that would fundamentally alter human consciousness over the vast timescales of interplanetary walking. Yet this silence isn't empty of information. The space between planets carries forms of energy and matter that tell stories about the history and nature of our solar system. The solar wind streams outward from our sun, carrying charged particles that interact with planetary magnetic fields in complex and beautiful ways. This invisible river of matter flows past our cosmic walker at speeds of several hundred kilometers per second, though it's so tenuous that it would feel like the faintest whisper. Cosmic rays, high-energy particles from distant stars and galaxies, streak through space at nearly the speed of light. These particles carry information about stellar explosions that occurred millions of years ago and thousands of light years away. They're constantly bombarding every square centimeter of space with a gentle but persistent radiation that tells the story of our galaxy's violent and creative processes. Our walker, moving at their steady 5 kilometers per hour, would be traveling through this invisible cosmic weather. Over the millennia of their journey, they would experience the slow cycles of solar activity, the 11-year rhythm of sunspot maxima and minima, and the longer-term variations in our star's energy output that influence the entire solar system. The Sun itself changes over these timescales. During a 100,000-year walk to Neptune, our star would experience roughly 9,000 complete solar cycles. Its magnetic field would flip thousands of times. Its surface would be constantly renewed by the churning convection of superheated plasma, and its total energy output would vary by fractions of a percent that nonetheless influence the climate and weather of every planet. These variations remind us that even the most stable-seeming aspects of our cosmic environment are constantly changing. The solar system isn't a static clockwork mechanism, but a dynamic, evolving system where every component influences every other component in ways both subtle and profound. The planets themselves are constantly moving through their orbits, creating an intricate gravitational choreography that unfolds over millions of years. Jupiter, the massive king of planets, acts like a cosmic vacuum cleaner, using its powerful gravitational field to capture or deflect asteroids and comets that might otherwise threaten the inner planets. This protective influence has been crucial to the development of life on Earth, but Jupiter's orbit isn't perfectly stable. Over very long timescales, the gravitational interactions between planets cause subtle changes in their orbital characteristics. These changes, known as orbital resonances and perturbations, mean that the solar system of today is subtly different from the solar system that existed 1 million years ago and will be different again 1 million years in the future. Our cosmic walker, taking their patient steps across these vast distances, would be moving through a solar system that's constantly, slowly changing around them. The destinations they're walking toward are themselves in constant motion, following elliptical paths through space that bring them closer to and farther from the Sun in regular, predictable cycles. This orbital motion adds another layer of complexity to our walking calculations. We've been using average distances for our journey times, but in reality, the distance to each planet is constantly changing. Mars, for example, can be as close as 55 million kilometers from Earth or as far as 400 million kilometers, depending on where both planets happen to be in their orbits when the measurement is taken. This means that the timing of our cosmic walk becomes crucial. A walker who began their journey to Mars when the planet was at its farthest point would face a journey lasting nearly 7,000 years. But someone fortunate enough to start when Mars was at its closest approach would reach their destination in a mere 1,200 years, saving more than 5 millennia of travel time. The elliptical nature of planetary orbits also means that our walker would experience the subtle gravitational influences of these worlds long before arriving at their surfaces. Earth's gravity, while faint, would still be detectable at distances of several million kilometers. As our traveller moved away from home, they would feel this invisible tether gradually weakening, their connection to humanity's birth world slowly fading into the cosmic background. Approaching each new planet would reverse this process. Millions of kilometers before arrival, the gravitational field of their destination would begin to influence their journey. For the gas giants like Jupiter and Saturn, this gravitational influence extends over truly vast distances, creating invisible spheres of influence that dwarf the planets themselves. Jupiter's gravitational field dominates a region of space more than 50 million kilometers in radius. Our walker would enter this sphere of influence while still farther from Jupiter than Earth is from the Sun. From that point forward, their journey would be shaped not just by their own steady pace, but by the growing gravitational pull of the giant planet ahead. This gravitational influence would create subtle but noticeable effects over the final years of the journey. Each step would become slightly easier as Jupiter's gravity began to accelerate our walker forward. The sensation would be incredibly gradual, perhaps imperceptible from day to day, but over months and years, the effect would become unmistakable. By the time our cosmic traveler reached Jupiter's cloud tops, after 13,000 years of walking, they would be falling toward the planet at an ever-increasing rate. Without some way to slow down, they would plunge into the thick atmosphere at tremendous speed, their long journey ending in a brief, brilliant meteor streak across Jupiter's perpetually stormy skies. This gravitational acceleration reveals something important about the nature of our solar system. The planets aren't just isolated worlds floating in empty space. They're connected by invisible fields of force that extend far beyond their visible surfaces. These gravitational fields shape the motion of everything in their vicinity, from tiny dust particles to massive asteroids, creating complex patterns of influence that astronomers are still working to fully understand. The spacecraft we send to explore the outer planets take advantage of these gravitational fields through a technique called gravity assist or gravitational slingshot. By carefully timing their approach to a planet, spacecraft can use that world's gravity to accelerate themselves toward their next destination, gaining speed and changing direction without burning any fuel. Our cosmic walker, moving at their constant 5 kilometers per hour, wouldn't be able to take advantage of these gravitational assists, but they would experience the same fundamental forces that guide our robotic explorers. Each planet they passed would tug at them gravitationally, slightly altering their path through space in ways that would accumulate over the vast timescales of their journey. These gravitational influences also explain why the outer planets are so much farther apart than the inner ones. In the early days of our solar system's formation, when planets were first condensing from the disk of dust and gas surrounding the young sun, the gravitational fields of the gas giants cleared out vast regions of space around their orbits. Jupiter and Saturn, in particular, acted like cosmic snowplows, sweeping up or scattering the material in their vicinity. This gravitational clearing process left behind the wide gaps we observe today between the outer planets. The same process that created these vast distances also ensured that the planet's orbits would remain stable over billions of years. This long-term stability is remarkable when we consider the complexity of the gravitational interactions involved. Each planet influences every other planet, creating a multi-body gravitational problem that mathematicians and astronomers have been working to solve for centuries. The fact that this system has remained stable for over 4 billion years, allowing time for life to evolve on Earth, represents one of the most fortunate accidents in cosmic history. Our walking journey through this stable but dynamic system reveals the profound interconnectedness of celestial mechanics. Every step our cosmic traveler takes occurs within a web of gravitational influences that extends throughout the solar system. The sun's gravity dominates the large-scale structure, keeping the planets in their orbits. But the planets' gravity influences each other, the asteroids, the comets, and even the paths of spacecraft and hypothetical cosmic walkers. This interconnectedness becomes most apparent when we consider the time our journey requires. A walk to Neptune lasting over 100,000 years would span roughly 600 complete orbits of that distant world around the Sun. During this time, Neptune would experience 600 seasonal cycles, each lasting about 40 years by Earth's measure. The seasonal changes on these distant worlds are subtle but real. Even at Neptune's vast distance from the Sun, the planet experiences variations in temperature and atmospheric activity as different hemispheres are tilted toward or away from our star. These seasonal cycles unfold so slowly that they would be barely perceptible to human observation, but they demonstrate that even the most remote planets participate in the rhythmic cycles that characterize our solar system. Uranus, with its extreme axial tilt, experiences the most dramatic seasons of any planet. For 42 Earth years at a time, one of its poles points almost directly at the Sun, while the other remains in constant darkness. Then, as Uranus continues its orbit, the illumination slowly shifts until the opposite pole enjoys its 42 years of continuous summer. Our walker approaching Uranus would witness these extreme seasonal transitions unfolding over decades of their journey. They would see the planet slowly rotating its orientation relative to the Sun, the pattern of light and shadow across its surface, shifting in a cosmic demonstration of how axial tilt creates seasons. These long seasonal cycles remind us that time itself operates differently in the outer solar system. What we experience as rapid change on Earth unfolds with glacial slowness at the distance of the gas giants. A single season on Neptune lasts longer than most human civilizations have existed. A complete seasonal cycle on Uranus spans nearly as long as the entire history of human agriculture. Yet, these slow rhythms are part of what makes the outer solar system so stable and predictable. The gravitational forces and orbital mechanics that govern planetary motion operate according to mathematical principles that remain constant across billions of years. Our cosmic walker, taking their patient steps across these vast distances, would be participating in patterns of motion and influence that extend far beyond human timescales. This stability also means that our journey calculations, while based on current planetary positions and distances, would remain accurate across the vast timescales involved. A walker beginning their journey to Neptune today would find that planet in almost exactly the predicted position when they arrived 100,000 years from now. The precision of celestial mechanics makes this level of prediction possible across timeframes that dwarf human experience. As our imaginary journey through the solar system draws toward its conclusion, we begin to see how these vast distances and timescales reshape our understanding of what it means to be human in a cosmic context. The universe operates on scales so large that our entire species' existence represents barely a moment in cosmic time, yet our minds can comprehend and calculate these scales with remarkable precision. The walking journey we've imagined tonight bridges the gap between human experience and cosmic reality. By breaking down impossible distances into the familiar rhythm of footsteps, we make the infinite feel manageable. Each calculated step becomes a meditation on distance, time, and the remarkable emptiness that defines our universe. In this emptiness, we discover not loneliness, but perspective. The vast spaces between worlds remind us that existence itself is rare and precious. The billions of years required for planets to form, for stars to ignite, for the complex chemistry of life to unfold, all depend on the patient, spacious architecture of the cosmos. Our Earth, tiny as it appears from the perspective of interplanetary distances, represents an almost miraculous convergence of favorable conditions. The right distance from the Sun for liquid water, the right size to maintain an atmosphere, the right magnetic field to deflect harmful radiation, the right moon to stabilize our planet's rotation. All of these factors had to align perfectly for our world to become the vibrant, life-bearing planet we know today. The walking journey to other worlds illuminates just how special and fragile this alignment truly is. Each planet we would visit on our cosmic pilgrimage represents a different outcome in the grand experiment of planetary formation. Venus shows us what happens when a greenhouse effect runs wild. Mars demonstrates the fate of a world that loses its atmosphere. The gas giants reveal what planets become when they form far from their star's warmth. Only Earth, among all the worlds we could walk to, maintains the delicate balance that allows complex life to flourish. This realization doesn't diminish the wonder of our cosmic journey, but enhances it, reminding us that we are not just observers of the universe, but active participants in its most remarkable achievement, the emergence of consciousness capable of contemplating its own cosmic context. As we conclude our gentle exploration of interplanetary walking, we're left with a profound sense of both human insignificance and human significance. Insignificant because the distances we've calculated dwarf not just individual human lives, but the entire span of our species' existence. Significant because we alone, among all the life we know of, can imagine these journeys, calculate these distances, and find meaning in the vast emptiness that surrounds our small, warm world. The rhythm of walking that has carried us through this meditation connects us to every human who has ever taken a journey, from the first tentative steps of our ancient ancestors to the confident strides of future generations who may one day actually travel to these distant worlds. Though the cosmic distances we've explored tonight remain forever beyond the reach of human feet, the human spirit that drives us to imagine such journeys will continue to carry us toward new horizons, new discoveries, and new ways of understanding our place in the infinite, patient, beautiful cosmos that surrounds us. In the gentle mathematics of footsteps and kilometers, we've found a way to make the universe feel both vast and intimate, both mysterious and comprehensible. And in that sweet contradiction lies perhaps the most human response to the cosmos, the recognition that we are small enough to be humble before infinity, yet large enough in spirit to embrace it with wonder, curiosity, and love. The mathematics we've explored tonight reveal something profound about the nature of existence itself. When we calculate walking times measured in millennia and geological epochs, we step outside the familiar boundaries of human experience and enter a realm where time flows, according to cosmic rhythms far grander than our own. Think for a moment about what it means to walk for 100,000 years. The very concept stretches our understanding beyond its natural limits. We measure our lives in decades, perhaps planning ahead, 1 or 2 generations. We remember our grandparents and hope to know our grandchildren. But a journey to Neptune would span more than 3,000 human generations, each passing the memory of this cosmic pilgrimage to the next like a sacred torch carried through the endless dark. The walkers who eventually reach Neptune's distant shores would be as different from those who began the journey as we are from our earliest ancestors who first discovered fire. Evolution itself operates on timescales shorter than our longest planetary walks. Over tens of thousands of generations, the human species would adapt to whatever impossible environment allows this cosmic journey to continue. Perhaps their bones would grow denser to handle the constant low-level radiation of interplanetary space. Maybe their hearts would strengthen to pump blood more efficiently in the reduced artificial gravity of our imagined space bridge. Their eyes might develop new sensitivities to detect the faint starlight that guides their way through the cosmic darkness. These adaptations would accumulate slowly, generation by generation, each change so subtle as to be imperceptible to any individual walker. But over the vast span of a journey to the outer planets, these tiny modifications would compound into something remarkable. The humans who finally set foot on Neptune's hypothetical surface might represent an entirely new branch of our species, shaped by the patient pressure of cosmic distance and time. Yet even as we contemplate these vast transformations, something essential would remain unchanged. The curiosity that drives us to imagine these journeys, the wonder that makes us look up at the night sky and ask what lies beyond our small world, the persistence that allows us to place one foot in front of the other, regardless of how far the destination might be. These qualities seem fundamentally human, likely to endure across any span of time or distance. The space between planets carries its own subtle beauty, invisible to our everyday experience, but profound in its implications. The vacuum that separates worlds isn't truly empty. It's filled with the gentle pressure of solar wind, streams of charged particles flowing outward from our sun at hundreds of kilometers per second. This invisible river carries the story of stellar fusion, the nuclear fire that transforms hydrogen into helium and releases the energy that warms our Earth. Our cosmic walker would move through this solar wind like a boat traveling upstream in a river too thin to feel. Over the millennia of their journey, they would experience the slow cycles of solar activity, the 11-year rhythm of sunspot maxima and minima that influences radio communications and creates the aurora on planets with magnetic fields. During solar maximum, when our star's magnetic field becomes tangled and chaotic, the solar wind grows stronger and more turbulent. Charged particles stream outward with increased intensity, creating space weather that affects every world in our solar system. During solar minimum, the wind becomes gentler and more steady, but it never stops completely. This constant flow of matter from the sun means that space isn't the perfect vacuum we might imagine. In every cubic centimetre of interplanetary space, there are roughly 5 particles, mostly protons and electrons, stripped from hydrogen atoms by the sun's intense heat. This is incredibly thin by Earth-bound standards, far more tenuous than the best vacuum we can create in laboratory chambers, but it's not absolute nothingness. These particles would interact with our walker in ways both subtle and profound. The gentle pressure of solar wind would create a constant, imperceptible force pushing them away from the sun. Over the vast timescales of interplanetary walking, this pressure might accumulate into a measurable effect, slightly lengthening the journey to inner planets while shortening the path to outer worlds. The radiation carried by these particles tells stories about our sun's interior. The nuclear furnace where hydrogen nuclei fuse together under unimaginable pressure and temperature. Each particle streaming past our cosmic traveller began its journey in the sun's core, where it took thousands of years to work its way outward through the dense stellar material. By the time these particles reach interplanetary space, they carry information about fusion reactions that occurred when human civilization was just beginning. Between the planets, space also carries the whisper of more distant stories. Cosmic rays, high-energy particles accelerated by supernova explosions and other violent stellar events, streak through our solar system at nearly the speed of light. These particles have travelled for millions of years across vast interstellar distances, carrying news of stellar deaths and births from regions of our galaxy we can barely see with our most powerful telescopes. Our walker would be constantly bathed in this gentle rain of cosmic information, each particle a messenger from the deep universe. Over the 100,000-year journey to Neptune, they would experience roughly 10 billion cosmic ray impacts, each one telling a story about stellar evolution, galactic structure, and the violent beauty of distant space. The cosmic ray flux varies as our solar system moves through different regions of our galaxy. When we pass through the local bubble, a region of space cleared by ancient supernova explosions, the cosmic ray intensity decreases. When we traverse denser regions where star formation is more active, the bombardment intensifies. Our cosmic walker would experience these galactic weather patterns unfolding over timescales that dwarf human civilization. This constant interaction with particles from across the universe reminds us that our solar system isn't isolated from the cosmos beyond. We're part of a vast galactic ecosystem, influenced by events that occurred millions of light years away and millions of years ago. The space between planets serves as a bridge connecting our small corner of the universe to the grand cycles of stellar birth and death that shape our entire galaxy. The temperature environment our walker would experience varies dramatically depending on their distance from the sun and their orientation relative to our star. Without an atmosphere to moderate temperature extremes, surfaces in space can swing from hundreds of degrees above freezing to hundreds of degrees below, sometimes within the span of minutes as they move from sunlight into shadow. Near Earth's orbit, a surface facing the sun directly would reach temperatures around 120 degrees Celsius, hot enough to boil water, But turn that same surface away from the sun, and it would cool rapidly to minus 170 degrees Celsius, cold enough to freeze carbon dioxide. This temperature swing of nearly 300 degrees represents one of the most extreme environments imaginable, far more hostile than anything found naturally on Earth's surface. As our walker moves toward the outer solar system, the sun's warming influence diminishes rapidly. At Jupiter's distance, even surfaces facing the sun directly would struggle to reach temperatures above minus 100 degrees Celsius. At Neptune's orbit, the sun appears as little more than a bright star, providing 1,000 times less energy per square meter than we receive on Earth. These temperature extremes would require our imagined space bridge to include not just breathable atmosphere, but also some form of temperature regulation. Perhaps the pathway itself would generate heat through some impossible mechanism. Or maybe our cosmic walker would need protective gear capable of maintaining comfortable temperatures across a 300-degree range, while remaining light enough for a journey lasting geological ages. The challenge of maintaining any technology across such vast timescales adds another layer of impossibility to our thought experiment. Even the most durable materials we know of would degrade over periods measured in millennia. Metals would slowly sublimate away in the vacuum of space. Plastics would become brittle under constant cosmic ray bombardment. Electronic systems would fail as their components gradually succumb to radiation damage and thermal cycling. Yet somehow, our imagined infrastructure must persist across timeframes longer than human civilization has existed. This requirement pushes us to consider what kinds of materials and systems could possibly endure such extreme longevity. Perhaps the space bridge would need to be self-repairing, constantly rebuilding itself from materials gathered from the solar wind and cosmic dust. Maybe it would need to be so massively over-engineered that even catastrophic failures would leave enough redundancy to continue functioning. The logistics of such a structure boggle the imagination. A bridge spanning the distance to Neptune would require more material than exists in all the asteroids in our solar system combined. The engineering challenges would dwarf any construction project ever attempted by human civilization. Yet for our peaceful thought experiment, we accept these impossibilities as the price of making cosmic distances comprehensible through the simple act of walking. As our cosmic walker moves through the outer solar system, they would witness phenomena that exist nowhere else in our immediate cosmic neighborhood. The magnetospheres of the gas giants create vast regions where charged particles from the solar wind become trapped and accelerated to enormous energies. These invisible magnetic bubbles extend millions of kilometers into space, creating radiation environments more intense than anything found near Earth. Jupiter's magnetosphere is particularly impressive, stretching across a region larger than the Sun itself. If we could see magnetic field lines with our naked eyes, Jupiter would appear as an enormous glowing structure in our sky, its magnetic influence reaching halfway to Saturn's orbit. Our walker approaching Jupiter would spend months traveling through this magnetic domain, experiencing radiation levels that would be lethal to unprotected human life within minutes. The interaction between Jupiter's magnetic field and its moons creates some of the most extreme environments in our solar system. Io, the innermost large moon, orbits through Jupiter's radiation belts and experiences particle bombardment so intense that it strips away atmospheric particles and creates a thin ionosphere of sulfur and oxygen. Europa and Ganymede also move through these radiation fields, though their greater distance from Jupiter provides some protection. These magnetic phenomena remind us that planets are more than just isolated spheres of rock or gas. They're complex systems that influence vast regions of space around them. The boundary between a planet and the space that surrounds it becomes blurred when we consider these invisible fields and their far-reaching effects. Saturn's magnetosphere, while smaller than Jupiter's, creates its own unique environment. The planet's magnificent rings lie within this magnetic bubble, and the interaction between charged particles and ring material creates a complex ecosystem of plasma dust, and electromagnetic radiation. Some of Saturn's moons orbit within the magnetosphere, while others venture beyond its protective influence into the unfiltered solar wind. The outer ice giants, Uranus and Neptune, have magnetic fields tilted at extreme angles relative to their rotational axes. This creates magnetospheres that tumble through space like cosmic corkscrews, generating complex patterns of charged particle acceleration and radiation emission. Our walker approaching these distant worlds would experience magnetic environments unlike anything found in the inner solar system. These magnetic complexities add another dimension to our understanding of what it truly means to travel between planets. The space around each world has its own character, its own invisible geography of forces and fields that would influence any traveler bold enough to venture into these remote regions. The gravitational environment of the outer solar system creates its own subtle but profound effects on our hypothetical journey. While we've calculated walking times based on constant speeds, the reality would be far more complex. Each planet's gravitational field extends far beyond its visible surface, creating invisible valleys and hills in the fabric of space-time itself. As our walker approaches Jupiter after 13 millennia of patient progress, they would begin to experience the giant planet's gravitational influence while still millions of kilometers away. Initially, this effect would be imperceptible, perhaps shortening each step by a few millimeters as Jupiter's gravity begins to accelerate our traveler forward. But over months and years, this acceleration would become increasingly noticeable. The final approach to Jupiter would transform from a walk into a controlled fall. Without some way to slow down, our cosmic traveler would plunge into the planet's thick atmosphere at tremendous speed, their long journey ending in a brief, brilliant meteor streak across Jupiter's perpetually stormy clouds. This gravitational acceleration reveals something important about the interconnected nature of our solar system. The planets aren't isolated islands floating in empty space. They're connected by invisible threads of gravitational influence that extend far beyond their physical boundaries. These connections create a complex web of forces that influences the motion of everything from tiny dust particles to massive asteroids, shaping the architecture of our entire planetary system. The spacecraft we send to explore the outer planets take advantage of these gravitational connections through carefully planned trajectory adjustments called gravity assists. By timing their approach to a planet precisely, spacecraft can use that world's gravity to accelerate themselves toward their next destination, gaining speed and changing direction without burning any fuel. Our cosmic walker, maintaining their steady pace regardless of gravitational influences, wouldn't benefit from these natural accelerations. But they would experience the same fundamental forces that guide our robotic explorers, feeling the subtle tug of each planet's gravity as they pass through its sphere of influence. These gravitational interactions also explain why the distances between planets increase so dramatically as we move outward from the Sun. During the formation of our solar system, when planets were first condensing from the disk of dust and gas surrounding the young Sun, the gravitational fields of the gas giants cleared out vast regions of space around their orbits. Jupiter and Saturn acted like cosmic snowplows, sweeping up or scattering the material in their vicinity. This gravitational clearing process left behind the wide gaps we observe today between the outer planets. The same forces that created these vast distances also ensured that the planets' orbits would remain stable over billions of years, allowing time for the complex chemistry of life to unfold on worlds like Earth. The long-term stability of planetary orbits is remarkable when we consider the complexity of the gravitational interactions involved. Each planet influences every other planet, creating what mathematicians call an n-body problem that has challenged scientists for centuries. The fact that this chaotic system has remained stable for over 4 billion years represents one of the most fortunate coincidences in cosmic history. Our walking journey through this stable but dynamic system reveals the profound interconnectedness of celestial mechanics. Every step our cosmic traveler takes occurs within a web of gravitational influences that extends throughout the solar system. The Sun's gravity dominates the large-scale structure, but the planet's gravitational fields shape the fine details of motion and trajectory. This interconnectedness becomes most apparent when we consider the time our journey requires. A walk to Neptune lasting over 100,000 years would witness roughly 600 complete orbits of that distant world around the Sun. During this time, all the planets would complete thousands of orbital cycles, their gravitational influences weaving together in patterns of incredible complexity and mathematical beauty. The seasonal cycles of the outer planets unfold over timeframes that challenge human comprehension. Neptune experiences seasons lasting about 40 Earth years each, with a complete seasonal cycle requiring 165 of our years. These slow rhythms mean that our cosmic walker would witness only a few complete seasonal transitions on any of the outer worlds during their entire journey. Uranus, with its extreme axial tilt, experiences the most dramatic seasons of any planet. For 42 Earth years at a time, one of its poles points almost directly at the Sun, while the other remains in constant darkness. Our walker approaching Uranus would see this extreme seasonal transition unfolding over decades, watching as the planet slowly reorients itself relative to the Sun. These glacial seasonal rhythms remind us that time itself operates differently in the outer solar system. What we experience as rapid change on Earth unfolds with geological slowness at the distances of the gas giants. A single season on Neptune lasts longer than most human institutions have existed. The complete seasonal cycle of Uranus spans nearly the entire history of human agriculture. Yet these slow rhythms contribute to the stability that makes planetary motion so predictable across vast timescales. The gravitational forces and orbital mechanics that govern planetary behavior operate according to mathematical principles that remain constant across billions of years. Our cosmic walker would be participating in patterns of motion that extend far beyond human experience into the deep time of geological and astronomical processes. This predictability means that our journey calculations, while based on current planetary positions, would remain accurate across the vast timescales involved. A walker beginning their journey to Neptune today would find that planet in almost exactly the predicted position when they arrived 100,000 years from now. The precision of celestial mechanics makes this level of prediction possible across timeframes that dwarf the entire history of human civilization. The constancy of physical laws across these immense scales provides a kind of cosmic comfort. While everything in human experience changes and evolves, the fundamental forces that govern planetary motion remain perfectly reliable. Gravity operates today exactly as it did billions of years ago, and will continue to operate billions of years in the future. The mathematical relationships that describe orbital motion are as eternal as anything in the universe we can observe. This reliability extends to the structure of atoms, the behavior of light, and the nuclear processes that power stars. The same physical constants that allow us to calculate walking times to distant planets also govern the fusion reactions in the Sun's core, the formation of chemical elements in stellar interiors, and the evolution of galaxies across cosmic time. Our cosmic walking journey connects us to these fundamental constants and processes. Each calculated step represents not just distance traveled, but participation in the basic physics that shapes everything from subatomic particles to galactic clusters. The simple act of walking, broken down into its component motions and energies, reveals the same physical principles that govern the motion of planets and stars. In this way, our thought experiment becomes more than just an exercise in mathematical calculation. It becomes a meditation on the unity of physical law across all scales of space and time. The forces that keep our feet planted on Earth's surface are the same forces that hold the planets in their orbits and the stars in their courses through the galaxy. The energy required to lift one foot and place it in front of the other draws on the same fundamental processes that power stellar fusion and drive galactic evolution. The simple rhythm of walking connects us to the deepest rhythms of the cosmos, the patient accumulation of small changes that eventually reshape entire worlds. As our imaginary journey draws toward its conclusion, we begin to see how the act of walking itself serves as a bridge between human experience and cosmic reality. Walking is perhaps the most fundamentally human form of movement, the locomotion that carried our ancestors across continents and into every environment on Earth. The rhythm of walking is encoded in our bodies and our minds. It's the pace at which we naturally explore the world around us, slow enough to observe details, but fast enough to cover meaningful distances over time. When we imagine walking to the planets, we're extending this most basic human capability into realms where it becomes both impossible and profound. The impossibility is obvious. No human could survive the journey or live long enough to complete it. The distances are too vast, the environment too hostile, the timeframes too extended for any biological organism to endure. Yet the profundity lies in what this impossibility reveals about the nature of space and time and our place within the cosmic order. By calculating how long these journeys would take at walking pace, we transform abstract astronomical distances into something our minds can process. The numbers become less intimidating when broken down into familiar units, like steps per hour and hours per day. Even a journey lasting 100,000 years becomes comprehensible when we imagine it as the accumulation of individual footsteps, each one moving us incrementally closer to our destination. This mental transformation allows us to develop an intuitive sense for the scale of our solar system. When we learn that Neptune is 4.5 billion kilometers away, the number is so large as to be meaningless. But when we calculate that walking there would take 100,000 years, we begin to grasp something essential about cosmic distance. 100,000 years encompasses the entire development of human consciousness, art, language, and technology. It's a time frame we can relate to through archaeological evidence and genetic analysis. We know what human life was like 100,000 years ago, and we can imagine how it might change over the next 100,000 years. By anchoring cosmic distances to these comprehensible time frames, we make the universe feel both vast and intimate. Vast because the distances are genuinely enormous, requiring geological ages to traverse at human speeds. Intimate because we can imagine the journey as an extension of something fundamentally human, the patient placing of one foot in front of the other. This intimacy with cosmic scale helps us develop what astronomers call cosmic perspective, an understanding of our place within the larger universe that influences how we think about ourselves and our world. When we truly grasp the distances to other planets, Earth begins to feel both precious and fragile, a small island of warmth and life in an ocean of cold emptiness. The walking meditation we've shared tonight illuminates this perspective gently, without overwhelming the mind with incomprehensible numbers or frightening concepts. Instead, it invites us to consider cosmic scale as an extension of human scale, connected by the simple rhythm of footsteps and the patient passage of time. In this gentle exploration, we discover that the universe is not an alien place separate from human experience. It's the context within which human experience unfolds, the vast stage upon which the drama of consciousness plays out. We are not observers looking at the cosmos from the outside. We are participants in cosmic evolution, made from stellar material and shaped by the same forces that govern planetary motion. The calcium in our bones was forged in the hearts of dying stars. The iron in our blood was created in supernova explosions that occurred billions of years ago. The water in our bodies has been cycling through Earth's hydrosphere for geological ages, falling as rain, flowing in rivers, and evaporating from oceans countless times. We are literally made of cosmic material, assembled into temporary patterns of complexity that can contemplate their own origins. The atoms that compose our bodies have existed since shortly after the Big Bang, and they will continue to exist long after our individual patterns dissolve back into the cosmic recycling system. This material connection to the cosmos means that our walking journey to the planets is not just a thought experiment. It's a recognition of our fundamental kinship with the universe that surrounds us. Every step we imagine taking through interplanetary space is a step taken by matter that was once part of stars, planets, and cosmic dust clouds. The carbon atoms in our muscles were once part of ancient atmospheres. The oxygen we breathe was released by countless generations of photosynthetic organisms. The hydrogen in our cells dates back to the earliest moments after the universe began, when the first atomic nuclei condensed out of the primordial fireball. When we walk on Earth, we're already participating in cosmic motion. Our planet rotates on its axis, carrying us through space at over 1,600 kilometers per hour at the equator. Earth orbits the Sun at nearly 30 kilometers per second, faster than any human vehicle has ever traveled. The entire solar system moves through the galaxy at over 200 kilometers per second, and the galaxy itself participates in the expansion of the universe. Every step we take on Earth's surface is simultaneously a step through interplanetary space, through the galaxy, and through the expanding cosmos. We are always in motion relative to the universe around us, always traveling at tremendous speeds, even when we feel perfectly still. Our imagined walk to the planets simply extends this motion in a particular direction, towards specific destinations that happen to be other worlds instead of other continents. The physical impossibility of such a journey doesn't diminish its conceptual value as a way of understanding our cosmic context. In the end, our gentle exploration of interplanetary walking distances reveals something beautiful about the relationship between human consciousness and cosmic scale. We are small enough to feel humble before the vastness of space, yet large enough in spirit to comprehend that vastness and find our place within it. The universe has evolved over billions of years to produce structures complex enough to understand themselves. In contemplating the distances to other planets, we participate in this cosmic self-awareness. We are the universe looking at itself, measuring itself, and marveling at its own immensity. This perspective transforms our understanding of what it means to be human. We are not accidental byproducts in an indifferent cosmos. We are expressions of the universe's capacity for complexity, beauty, and understanding. Our consciousness represents one of the most remarkable achievements in cosmic evolution, the emergence of matter organized in such a way that it can contemplate its own origins and destiny. The walking journey we've imagined tonight connects us to this larger story. Each calculated step represents not just distance traveled, but participation in the ongoing adventure of cosmic evolution. We are walking not just through space, but through time, through the history of matter and energy that has led to this moment of awareness and wonder. As we settle into the quiet conclusion of our cosmic walk, let the rhythm of distant footsteps carry you toward rest. In your dreams tonight, perhaps you'll find yourself walking slowly through the star-filled darkness, moving at your own gentle pace toward worlds beyond imagination. Each step you take in those dreams will carry you deeper into the peaceful understanding that we are all cosmic walkers, temporary arrangements of ancient starlight, making our way through the universe with curiosity, courage, and wonder. The planets will continue their ancient orbits, the stars will pursue their courses through the galaxy, and the universe will expand into whatever future awaits. And somewhere in that vast cosmic story, your own small journey continues, step by step, breath by breath, connected to everything that was, everything that is, and everything that ever will be. Rest well, fellow travelers. The cosmos is patient, and there is time enough for all the journeys we can imagine, and many more we have yet to dream. Yet to dream. In the quiet depths of our cosmic journey, we encounter something that fundamentally changes how we perceive distance and time. The space between the inner planets and the gas giants reveals itself as more than just emptiness. It contains the asteroid belt, a region that stretches across millions of kilometers, filled with the remnants of planetary formation that never quite coalesced into a world. Walking through the asteroid belt would be like crossing a vast desert where the grains of sand are boulders and mountains, scattered so far apart that you might walk for months without seeing a single one. The belt extends from about 300 million kilometers to 500 million kilometers from the Sun, creating a boundary between the familiar rocky worlds and the mysterious realm of the giants beyond. At our gentle walking pace of 5 kilometers per hour, crossing even the narrowest part of this region would require nearly 4,000 years. 4 millennia of placing one foot in front of the other through a space so vast that the asteroids, despite their fearsome reputation in popular imagination, are actually separated by distances measured in millions of kilometers. The largest asteroid, Ceres, is nearly 1,000 kilometers in diameter, big enough to be classified as a dwarf planet. Yet even Ceres would appear as nothing more than a distant star during most of our passage through the belt. The asteroids that populate this region are the scattered pieces of a world that might have been, prevented from forming by Jupiter's immense gravitational influence. As we emerge from the asteroid belt and continue our patient journey toward Jupiter, the nature of space itself begins to change around us. The Sun, which has been our constant companion throughout the inner solar system, begins to appear smaller and more distant. Its warming rays carry less energy at this distance, and the cosmic environment grows colder and more alien with each passing year. Jupiter's gravitational influence extends far beyond the asteroid belt, creating invisible currents in space that guide the motion of comets and asteroids across the entire outer solar system. Our walker would begin to feel this influence while still tens of millions of kilometers from the planet itself, a gentle but persistent tug that grows stronger with each step. The approach to Jupiter after 13,000 years of walking would reveal a world so vast that it challenges our understanding of what a planet can be. Jupiter contains more than twice as much matter as all the other planets combined. Its great red spot, a storm that has raged for centuries, is larger than our entire Earth. The planet's 4 largest moons, discovered by Galileo over 400 years ago, are worlds in their own right, each with unique characteristics that rival anything in the inner solar system. Io, the innermost of these large moons, is the most volcanically active body known in the solar system. Its surface is constantly renewed by sulfur compounds erupting from hundreds of active volcanoes. Europa, covered by a smooth shell of ice, likely harbours a liquid ocean beneath its frozen surface that may contain more water than all of Earth's oceans combined. Ganymede, larger than the planet Mercury, possesses its own magnetic field and may also harbour subsurface oceans. Callisto, scarred by billions of years of impacts, preserves a record of the violent early history of our solar system. Each of these moons would appear as a distinct world to our cosmic walker, growing from points of light to visible disks as the long journey to Jupiter nears its end. The radiation environment around Jupiter creates one of the most hostile regions in the solar system. The planet's powerful magnetic field traps charged particles from the solar wind, accelerating them to tremendous energies. This radiation would be lethal to unprotected human life within minutes, adding another layer of impossibility to our already impossible journey. Yet in our peaceful thought experiment, we continue walking, protected by whatever miraculous technology allows this cosmic pilgrimage to proceed. The final approach to Jupiter would transform the planet from a bright star to a vast disk that fills more and more of the sky, its bands of clouds becoming visible to the naked eye, its great storms revealing their intricate structure and timeless beauty. Standing at Jupiter's cloud tops after 13 millennia of patient travel, our cosmic walker would witness weather systems that dwarf anything on Earth. Winds reaching speeds of several hundred kilometers per hour create bands and zones that circle the planet in patterns of mathematical precision. The Great Red Spot, a high-pressure storm system larger than Earth, would appear as a vast crimson eye staring back into space. But Jupiter has no solid surface on which to stand. The planet is composed almost entirely of hydrogen and helium under tremendous pressure. As our walker descended into the thick atmosphere, the gas would gradually become denser and denser until it transformed into liquid, then eventually into a metallic form of hydrogen that exists nowhere else in the solar system. Deep within Jupiter's interior, pressures reach millions of times greater than Earth's atmospheric pressure. At the very center, there may be a rocky core, roughly the size of our entire planet, but compressed to densities that would make the heaviest materials on Earth seem light as air. This core, if it exists, remains forever hidden beneath thousands of kilometers of metallic hydrogen and liquid gas. The journey from Jupiter to Saturn represents another doubling of distance, another leap into the realm of truly cosmic proportions. Saturn orbits at approximately twice Jupiter's distance from the Sun, adding another 14,000 years to our walking journey. The accumulated travel time to reach Saturn approaches 27,000 years, a span that encompasses the entire development of human agriculture and civilization. Saturn itself presents one of the most beautiful sights in the solar system. Its magnificent ring system, composed of countless particles of ice and rock, creates a structure so thin relative to its diameter that it would be invisible if viewed edge-on, yet so extensive that it spans a distance greater than the space between Earth and its moon. The rings are not solid structures, but collections of individual particles, each following its own precise orbit around Saturn. Some particles are as small as dust grains, others as large as houses or small mountains. They move in perfect harmony according to the mathematical laws of orbital mechanics, creating gaps and divisions that reveal the subtle gravitational influences of Saturn's many moons. The ring system itself tells a story of cosmic violence and beauty. These particles may be the remains of a moon that wandered too close to Saturn and was torn apart by tidal forces, or they might be leftover material from the formation of the solar system itself. Whatever their origin, they create a structure of such delicate beauty that it seems almost too perfect to exist in the harsh environment of space. Saturn's largest moon, Titan, is larger than the planet Mercury and possesses a thick atmosphere composed primarily of nitrogen. This atmosphere creates weather patterns including rain, but the rain consists of liquid methane rather than water. Lakes and rivers of liquid hydrocarbons dot Titan's surface, creating an alien hydrological cycle that mirrors Earth's water cycle, but operates at temperatures cold enough to freeze nitrogen solid. Enceladus, another of Saturn's moons, erupts geysers of water ice from its south polar region, suggesting the presence of a subsurface ocean kept liquid by the gravitational flexing caused by Saturn's powerful gravity. These geysers create a thin ring around Saturn as the ice particles spread along Enceladus's orbital path, demonstrating how even small moons can influence the structure of planetary ring systems. The approach to Saturn would reveal these moons one by one, each growing from a point of light to a visible world with its own unique characteristics. Our cosmic walker, having travelled for nearly 300 centuries, would witness the slow dance of these satellites as they orbit their giant parent, each following paths determined by gravitational forces that have remained unchanged for billions of years. The view from Saturn's cloud tops would encompass a vista unlike anything else in the solar system. The rings would stretch across the sky in magnificent arcs, their structure varying from dense opaque bands to regions so transparent that stars would be visible through them. The interplay of light and shadow as Saturn rotates would create an ever-changing display of cosmic artistry. Beyond Saturn, the distances to the remaining planets stretch into realms that challenge even our expanded understanding of cosmic scale. Uranus, the tilted ice giant, orbits at nearly twice Saturn's distance from the Sun, requiring an additional 38,000 years of walking to reach. The cumulative journey time to Uranus approaches 65,000 years, a span that encompasses the entire history of modern human behavior. Uranus rotates on its side, rolling along its orbital path like a cosmic bowling ball. This extreme axial tilt means that each pole of Uranus experiences 42 years of continuous sunlight followed by 42 years of continuous darkness. The planet's seasons unfold over timescales that dwarf human generations, creating climate patterns that operate according to rhythms far removed from anything we experience on Earth. The ice giants, Uranus and Neptune, represent a different class of planet altogether. Unlike the gas giants Jupiter and Saturn, which are composed primarily of hydrogen and helium, the ice giants contain substantial amounts of water, methane, and ammonia ices. These materials exist under such extreme pressure and temperature that they behave more like hot, dense fluids than the familiar ice we know on Earth. Uranus appears as a nearly featureless blue-green disk through telescopes, its atmosphere lacking the dramatic bands and storms that characterize Jupiter and Saturn. This apparent tranquility is deceptive, however. The planet's extreme axial tilt creates atmospheric dynamics unlike anywhere else in the solar system, with complex circulation patterns that astronomers are still working to understand. The magnetic field of Uranus is tilted at an extreme angle relative to the planet's rotation axis, creating a magnetosphere that tumbles through space like a cosmic corkscrew. This unusual configuration suggests that Uranus may have suffered a catastrophic collision early in its history, an impact so violent that it knocked the planet onto its side and scrambled its internal structure. As our cosmic walker approaches Uranus after 65 millennia of patient travel, they would witness the slow progression of this strange world's seasons. Over the decades of their final approach, they might see the planet gradually reorienting itself relative to the Sun, the pattern of illumination across its surface shifting as the seasons change with geological slowness. The journey from Uranus to Neptune, the final leg of our interplanetary pilgrimage, adds another 37,000 years to our walking time. Neptune, the most distant of the major planets, orbits at an average distance of nearly 4.5 billion kilometers from Earth. Reaching this remote world requires approximately 102,000 years of continuous walking, a time frame that spans the entire development of human consciousness, art, language, and technology. Neptune presents a world of paradox and mystery. Despite receiving only 1,000th of the sunlight that Earth receives, Neptune experiences some of the most violent weather in the solar system. Winds reach speeds of over 2,000 kilometers per hour, faster than the speed of sound on Earth. The energy driving these incredible storms comes not from solar heating, but from the planet's own internal heat source, a reminder that worlds can possess their own internal dynamics, independent of their star's influence. The deep blue color of Neptune comes from methane in its atmosphere, which absorbs red light and reflects blue wavelengths back into space. This creates a world that appears as a brilliant sapphire when viewed through telescopes, a jewel-like beauty that seems almost too perfect for such a remote and hostile environment. Neptune's largest moon, Triton, orbits the planet in a retrograde direction, moving opposite to Neptune's rotation. This unusual orbital characteristic suggests that Triton was once an independent object, possibly similar to Pluto, that was captured by Neptune's gravity at some point in the distant past. Triton possesses a thin atmosphere and active geysers that erupt nitrogen gas and dark particles high into its tenuous sky. The approach to Neptune after more than 1,000 centuries of walking would reveal a world of stunning beauty and alien majesty. The planet's deep blue atmosphere would gradually resolve into bands and zones, though far more subtle than those of Jupiter or Saturn. Great storms would appear and disappear over the decades of approach, their life cycles measured in years rather than the centuries-long persistence of Jupiter's great red spot. Standing at Neptune's cloud tops, our cosmic walker would witness the culmination of an impossible journey through space and time. The sun would appear as little more than a bright star, providing virtually no warmth to this distant world. The view would encompass a perspective on the solar system available to no human eyes, a vantage point from which Earth would be completely invisible, lost in the glare of our distant star. The winds of Neptune would rage around our imaginary visitor at speeds that would tear apart any earthly structure within seconds. Yet in the peaceful impossibility of our thought experiment, we stand witness to the raw power and beauty of planetary atmospheres, operating according to physical principles that remain constant across the entire universe. From Neptune's perspective, the solar system appears as a vast collection of worlds scattered across immense distances, with the inner planets huddled close to the sun's warmth and the outer giants separated by gaps that dwarf the distances between continents on Earth. The architecture of our planetary system reveals itself as a structure built on scales that challenge human comprehension, yet operate according to mathematical principles we can understand and predict. The journey we have completed in our imagination spans more than 4 billion kilometers and over 100,000 years of walking. This vast pilgrimage carries us through realms of space, where human intuition breaks down and cosmic perspective begins to emerge. We have walked through the entire development of human civilization, from the first agricultural settlements to the space age and far beyond. Yet even this monumental journey represents only a tiny fraction of the distances that separate our solar system from the nearest stars. The journey to Proxima Centauri, our closest stellar neighbour, would require over 60 million years of walking. The distances to other star systems stretch into timeframes measured in hundreds of millions or billions of years, spans that encompass the entire evolution of complex life on Earth. These cosmic distances remind us that space is not just big, it is almost entirely empty. The matter that makes up planets, stars, and galaxies represents less than 5% of the universe's total content. The vast majority of cosmic space is filled with dark matter and dark energy, mysterious components that we can detect only through their gravitational effects on the matter we can observe. This emptiness is not a flaw in the universe's design, but a fundamental requirement for the existence of structure and complexity. Without these vast spaces between celestial bodies, gravitational interactions would quickly become chaotic. Planetary orbits would be unstable, stars would collide frequently, and the delicate processes that allow life to develop and flourish would be impossible. The emptiness of space also ensures that light can travel across cosmic distances without obstruction, carrying information about distant stars and galaxies across billions of years. This transparency allows us to observe the universe's history, seeing galaxies as they existed when the cosmos was young and stellar formation was just beginning. Our walking meditation through the solar system connects us to these vast scales and timeless processes. Each calculated step represents participation in the fundamental physics that governs everything from atomic interactions to galactic evolution. The simple rhythm of placing one foot in front of the other becomes a metaphor for the patient accumulation of small changes that eventually reshape entire worlds. Walking itself represents one of humanity's most fundamental capabilities, the locomotion that carried our ancestors across continents and into every environment on Earth. When we extend this basic human activity into the realm of interplanetary space, we create a bridge between the familiar and the cosmic, making the infinite feel somehow manageable through the simple persistence of forward motion. The impossibility of actually walking to other planets doesn't diminish the value of this thought experiment. Instead, it illuminates the true nature of cosmic distances and the remarkable achievement represented by the space missions that have actually visited these distant worlds. Every spacecraft we have sent to explore the outer planets has accomplished something that would require tens of thousands of years to achieve at walking pace. The Voyager spacecraft, launched in 1977, reached Neptune in just 12 years by taking advantage of a rare alignment of the outer planets that occurs only once every 176 years. These robotic explorers have compressed our walking journeys into practical mission timelines, returning images and data that reveal the true nature of worlds we could never visit in person. Yet the data returned by these missions confirms the accuracy of our walking calculations. The distances are exactly as vast as we have calculated, the environments exactly as hostile as we have described. The universe operates according to physical laws that remain constant across all scales of space and time, allowing us to predict with precision the location of planets thousands of years in the future, or the energy requirements for journeys we may never actually attempt. This reliability of physical law across cosmic scales provides a kind of fundamental comfort. While everything in human experience changes and evolves, the forces that govern planetary motion remain perfectly predictable. The same gravitational equations that describe the fall of an apple also govern the orbits of planets and the formation of galaxies. Our cosmic walking journey reveals this unity of physical principle across all scales of existence. The energy required to lift one foot and place it in front of the other draws on the same fundamental forces that power stellar fusion and drive cosmic evolution. In contemplating these connections, we discover that we are not separate from the universe, but integral participants in its ongoing development. The atoms that compose our bodies were forged in the nuclear furnaces of ancient stars. The calcium in our bones, the iron in our blood, the oxygen we breathe, all originated in stellar interiors where temperatures and pressures created the elements necessary for complex chemistry. We are literally made of star material, temporarily organized into patterns capable of contemplating their own cosmic origins. This material connection to the cosmos means that our imagined journey to the planets represents more than just a mathematical exercise. It acknowledges our fundamental kinship with the universe that surrounds us. Every step we imagine taking through interplanetary space is a step taken by matter that was once part of stars, planets, and cosmic dust clouds. When we walk on Earth, we are already participating in cosmic motion. Our planet spins on its axis, carrying us through space at tremendous speed. Earth orbits the Sun at nearly 30 kilometers per second, and the entire solar system moves through the galaxy at over 200 kilometers per second. We are always in motion relative to the universe around us, always traveling at cosmic speeds, even when we feel perfectly still. Our imagined walk to the planets simply extends this motion in a specific direction, toward particular destinations that happen to be other worlds instead of other continents. The physical impossibility of such a journey doesn't diminish its value as a tool for understanding our place in the cosmic order. In the end, our gentle exploration of interplanetary walking distances reveals something profound about the relationship between human consciousness and cosmic scale. We exist at a unique position in the hierarchy of size and complexity, large enough to contemplate galaxies yet small enough to appreciate the intricate beauty of individual atoms. Our minds can encompass the vast distances we have calculated tonight, yet we remain grounded in the immediate reality of our own bodies and the familiar rhythm of our own footsteps. This dual perspective allows us to feel both humbled by cosmic immensity and amazed by our own capacity to understand and appreciate that immensity. The universe has evolved over billions of years to produce structures complex enough to understand themselves. In contemplating the distances to other planets, we participate in this cosmic self-awareness. We are the universe examining itself, measuring its own dimensions, and marveling at its own intricate beauty. This perspective transforms our understanding of what it means to be human. We are not accidental byproducts in an indifferent cosmos, but expressions of the universe's capacity for complexity, consciousness, and wonder. Our ability to imagine walking to distant worlds represents one of the most remarkable achievements in cosmic evolution. The walking journey we have shared tonight connects us to this larger story of cosmic development. Each step we have calculated represents not just distance traveled, but participation in the ongoing adventure of universal evolution. We are walking not just through space, but through the history of matter and energy that has led to this moment of awareness and understanding. As our cosmic meditation draws to its peaceful conclusion, let the rhythm of imagined footsteps carry you toward rest. The planets continue their ancient orbits according to laws that will persist long after our brief moment of consciousness has passed. Yet in contemplating these eternal rhythms, we touch something timeless within ourselves. The distances we have explored tonight will remain constant for millions of years to come. Future generations may develop technologies that make interplanetary travel as routine as crossing oceans has become for us. But the fundamental scales we have discovered will endure, reminding all conscious beings of their place within the vast and patient cosmos. In your dreams tonight, perhaps you will find yourself walking slowly through star-filled darkness, moving at your own gentle pace toward worlds beyond imagination. Each step in those dreams will carry you deeper into the peaceful understanding that we are all cosmic travelers, temporary arrangements of ancient starlight making our way through the universe with curiosity, courage, and wonder. The cosmos is patient, and there is time enough for all the journeys we can imagine, and many more we have yet to dream. Rest well, fellow travelers, knowing that you are part of something magnificent and eternal, connected to everything that was, everything that is, and everything that ever will be. The gentle mathematics of cosmic distance continues to unfold before us as we venture deeper into the outer reaches of our solar system. Beyond Neptune lies a realm that challenges even our expanded understanding of space and time, a region where the very concept of walking becomes not just impossible, but almost meaningless in the face of such overwhelming emptiness. Yet even here, in these most remote corners of our planetary neighborhood, we can continue our patient calculations. Beyond Neptune's orbit lies Pluto, no longer classified as a major planet, but still a world worthy of our consideration. This distant dwarf planet follows an elliptical path that carries it between 4.4 and 7.4 billion kilometers from the Sun, sometimes bringing it closer than Neptune, sometimes carrying it far beyond. Walking to Pluto at its average distance would require approximately 140,000 years of continuous movement. This timeframe encompasses not just the entire development of human civilization, but extends deep into our evolutionary past. If our earliest ancestors had begun walking to Pluto when they first developed the capacity for abstract thought, that journey would still be continuing today, with tens of thousands of years remaining before arrival. Pluto itself represents a world of perpetual twilight, where high noon resembles deep dusk on Earth. The Sun appears as nothing more than a bright star in Pluto's sky, providing 1,000 times less light than we receive on our home planet. Surface temperatures hover around minus 230 degrees Celsius, cold enough to freeze nitrogen solid and create an atmosphere so thin that it would be imperceptible to human senses. The landscape of Pluto reveals itself through our most sophisticated telescopes as a world of surprising complexity and beauty. Heart-shaped plains of nitrogen ice stretch across regions larger than Texas. Mountains of water ice, as hard as stone at these temperatures, rise several kilometers above the surrounding terrain. The interplay of light and shadow across this alien topography creates patterns of subtle beauty that speak to the underlying physical processes that shape all worlds. Pluto's largest moon, Charon, orbits so close to the dwarf planet that the two worlds are tidally locked, always showing the same face to each other as they dance through their distant orbit. This binary system represents one of the most elegant examples of gravitational interaction in our solar system. Two worlds locked in an eternal embrace as they circle the Sun together. But even Pluto does not mark the true edge of our solar system's influence. Far beyond the orbit of this distant world lies the Kuiper Belt, a vast region populated by thousands of small, icy bodies left over from the formation of our planetary system. These objects, ranging in size from tiny fragments to worlds nearly as large as Pluto itself, follow elliptical paths that carry them across a region extending to more than 50 times Earth's distance from the Sun. Walking to the inner edge of the Kuiper Belt would require approximately 200,000 years of continuous movement. This journey would span a time frame longer than our species has existed in its current form. The humans who eventually reach this distant realm would be as different from us as we are from our earliest ancestors who first began to use tools and create art. The Kuiper Belt objects themselves tell stories about the early history of our solar system. These ancient remnants preserve materials and structures that date back to the very beginning of planetary formation, when our entire solar system was nothing more than a disk of dust and gas surrounding the young sun. In their chemical composition and physical characteristics, we can read the history of how worlds are born from cosmic debris. Some Kuiper Belt objects follow paths so elliptical that they venture far beyond the belt's main population, carrying them into the even more remote region known as the scattered disk. These distant wanderers can reach distances of 100 to 150 times Earth's distance from the Sun, requiring walking times that stretch beyond 500,000 years. Such timeframes begin to approach the limits of human comprehension. 500,000 years encompasses not just the entire span of human civilization, but reaches back to times when our ancestors were still developing the basic cognitive capabilities that define our species. The walkers who might eventually reach these distant objects would represent evolutionary changes accumulated across thousands of generations. Yet even these vast distances pale in comparison to what lies beyond. At the very edge of our solar system's gravitational influence extends the Oort cloud, a spherical shell of cometary nuclei that may contain trillions of individual objects. This vast reservoir of cosmic debris extends to distances of 50,000 to 100,000 times Earth's distance from the Sun, creating a boundary that truly marks the edge of our solar system's domain. Walking to the inner edge of the Oort cloud would require approximately 10 million years of continuous movement. This time frame exceeds not just human history, but approaches the timescales of geological and evolutionary change. 10 million years ago, our planet's continents were arranged differently. Its climate was warmer, and our own evolutionary lineage was just beginning to diverge from other great apes. The Oort cloud itself represents one of the most mysterious regions of our solar system. So distant that individual objects cannot be detected by even our most powerful telescopes, its existence is inferred from the orbital characteristics of long-period comets that occasionally venture into the inner solar system. These cosmic visitors, with their spectacular tails of gas and dust, carry materials from the very edge of our Sun's gravitational influence. When gravitational perturbations from passing stars or galactic tidal forces disturb objects in the Oort cloud, some begin the long journey towards the inner solar system. This journey can take millions of years to complete, carrying these ancient fragments from the frozen darkness at the edge of space into the warming light of our Sun. The comets we observe from Earth represent messengers from these distant realms, bringing samples of material that has remained virtually unchanged since the formation of our solar system. In their ice and dust, we can study the chemical composition of the primordial solar nebula, learning about conditions that existed over 4.5 billion years ago. Our imagined walk to the Oort cloud would carry us not just through space, but through deep time, into regions where the very concept of our solar system begins to blur into the interstellar medium. At these distances, our Sun's gravitational influence becomes so weak that it competes with the gravitational effects of nearby stars and the galaxy itself. The boundary between our solar system and interstellar space is not sharp, but gradual, extending across a region where solar influence slowly fades into the background gravitational environment of our local stellar neighborhood. This transition zone, known as the heliosheath, marks where the solar wind finally succumbs to the pressure of the interstellar medium. walking beyond even the Oort cloud, we would eventually reach truly interstellar space, the vast emptiness that separates our solar system from the nearest stars. The closest star to our Sun, Proxima Centauri, lies at a distance of approximately 40 trillion kilometers. Walking to this nearest stellar neighbor would require over 90 million years of continuous movement. Such a journey would span timeframes that encompass the entire evolution of complex life on Earth. 90 million years ago, dinosaurs ruled our planet. Flowering plants were just beginning to diversify, and the continents were arranged in configurations quite different from today. The walkers who might eventually reach Proxima Centauri would represent changes accumulated across geological time. These interstellar distances reveal the true isolation of our solar system within the galaxy. The space between stars is so vast that even light, traveling at 300,000 kilometers per second, requires over 4 years to bridge the gap to our nearest stellar neighbor. Radio signals sent to Proxima Centauri would take more than 4 years to arrive, making any conversation across interstellar distances a correspondence measured in decades rather than minutes. The galaxy itself contains over 100 billion stars, each potentially surrounded by its own family of planets. Yet the distances between these stellar systems are so immense that our galaxy, despite containing this multitude of stars, is over 99.9% empty space. The stellar density is so low that if our galaxy were scaled down to the size of a continent, individual stars would be separated by distances measured in kilometers. This vast emptiness is fundamental to the stability and longevity of stellar systems. Without these enormous gaps between stars, gravitational interactions would quickly disrupt planetary orbits, making the long-term stability necessary for the evolution of life virtually impossible. The cosmic architecture that seems so lonely from our perspective is actually essential for creating environments where complexity and consciousness can develop. Our walking meditation through these cosmic distances helps us appreciate the remarkable chain of circumstances that led to our existence. The precise balance of forces that keeps planets in stable orbits, the careful spacing of stellar systems that prevents gravitational chaos, the long timescales that allow evolutionary processes to unfold, all contribute to creating conditions suitable for the emergence of life and consciousness. The Earth on which we live represents an almost impossibly rare convergence of favorable conditions within this vast cosmic architecture. The right distance from the Sun for liquid water to exist, the right size to maintain a substantial atmosphere, the right magnetic field to deflect harmful radiation, the right moon to stabilize our planet's rotation, and create tides that may have been crucial for the development of life. When we consider the walking times we have calculated tonight, from the mere decades required to reach our moon to the millions of years needed to reach nearby stars, we begin to understand just how special our small corner of the universe truly is. We exist on a world that happens to orbit within the narrow zone around our star where liquid water can exist, in a solar system stable enough to maintain these conditions for billions of years. This perspective doesn't diminish our significance, but enhances it, revealing that we are not accidents in an indifferent cosmos, but expressions of the universe's capacity to create complexity, beauty, and understanding. The consciousness that allows us to contemplate these vast distances represents one of the most remarkable achievements in cosmic evolution. Matter organized in such a way that it can examine and appreciate its own origins. The walking rhythm we have used throughout our journey tonight connects us to something fundamental about human nature and our relationship with distance and time. Walking is perhaps our most basic form of exploration, the locomotion that carried our ancestors across continents and into every habitable environment on Earth. It represents patience, persistence, and an inherent optimism that any distance, no matter how great, can eventually be overcome through steady effort. When we apply this most human of activities to cosmic distances, we create a bridge between the familiar and the infinite. The impossibility of actually walking to other planets doesn't diminish the value of this thought experiment. Instead, it illuminates the true nature of space and time, while making these abstract concepts feel somehow manageable through the simple persistence of placing one foot in front of the other. Each step in our imagined journey represents more than just distance covered. It symbolizes the patient accumulation of small changes that eventually reshape entire worlds. The gradual processes that create mountains, carve canyons, and allow life to evolve from simple chemicals into conscious beings capable of contemplating their own existence. The cosmic distances we have explored reveal themselves to be not empty voids, but structured hierarchies of space and time. From the familiar scale of our daily walks to the planetary distances that require millennia to traverse, from the stellar separations that demand millions of years to the galactic scales that stretch across billions of years, each level of cosmic architecture operates according to the same fundamental physical laws. These laws provide a kind of cosmic constancy that transcends the temporary nature of individual lives and civilizations. Gravity operates today exactly as it did billions of years ago and will continue to operate billions of years in the future. The mathematical relationships that describe orbital motion are as eternal as anything we can observe in the universe. This reliability extends to all the fundamental forces and constants that govern cosmic behavior. The speed of light remains constant across all of space and time. The strength of electromagnetic and nuclear forces never varies. The properties of atoms and molecules remain consistent throughout the observable universe, allowing the same chemical processes that created life on Earth to potentially operate on distant worlds. Our cosmic walking journey connects us to these eternal principles while remaining grounded in the immediate reality of human experience. We are simultaneously tiny specks in a vast universe and conscious participants in the grandest story ever told. The evolution of matter and energy from simplicity to complexity, from chaos to consciousness. The rhythm of footsteps that has guided our meditation tonight echoes the deeper rhythms of cosmic evolution. The patient accumulation of distance through steady walking mirrors, the patient accumulation of complexity through cosmic time. Stars form slowly from gravitational collapse. Planets cool gradually from molten beginnings. Life evolves incrementally from simple to complex forms. Each of these processes operates according to the same principle that guides our imagined cosmic walk: the persistent application of small changes over vast timescales. The universe builds its most magnificent structures not through sudden dramatic events, but through the quiet patience of physical law operating across billions of years. This perspective reveals something profound about the nature of achievement and understanding. The greatest discoveries and accomplishments often result not from sudden inspiration, but from sustained effort applied consistently over long periods. The scientific understanding that allows us to calculate planetary distances and orbital mechanics developed through centuries of careful observation and mathematical analysis. The space missions that have actually visited the distant worlds, we have imagined walking to represent the culmination of decades of technological development and international cooperation. Each successful mission builds upon the achievements of previous explorers, creating a gradual accumulation of knowledge and capability that eventually makes the impossible seem routine. Our ability to contemplate cosmic distances and imagine journeys across interplanetary space reflects this same patient development of human consciousness and understanding. The cognitive capabilities that allow us to think about million-year journeys and billion-kilometer distances evolved slowly over hundreds of thousands of years of human development. The languages we use to describe these concepts, the mathematical tools we employ to calculate walking times, the scientific instruments that reveal the true nature of distant planets, all represent achievements built through the sustained effort of countless generations of human thinkers and creators. In this way, our cosmic walking meditation becomes more than just an exercise in mathematical calculation. It becomes a celebration of human achievement and a recognition of our deep connection to the universe that surrounds us. We are not separate observers looking at the cosmos from outside, but integral participants in its ongoing development. The atoms that compose our bodies were forged in stellar interiors billions of years ago. The calcium in our bones, the iron in our blood, the oxygen we breathe, all originated in nuclear reactions that occurred in the hearts of ancient stars. When those stars exhausted their fuel and exploded as supernovae, they scattered these elements across space, eventually incorporating them into new stars, planets, and ultimately into the chemical structures that make life possible. We are literally made of star material, temporarily organized into patterns capable of contemplating their own cosmic origins. This material connection to the universe means that our imagined journey to the planets represents more than just a thought experiment. It acknowledges our fundamental kinship with the cosmos itself. Every step we have calculated tonight is a step taken by matter that was once part of stellar cores, planetary surfaces, and cosmic dust clouds. The carbon atoms in our muscles, the hydrogen in our cells, the trace elements that make our bodies function, all have histories that extend back to the earliest moments of cosmic evolution. This deep connection suggests that our cosmic walking meditation is not just about distance and time, but about coming home to our true nature as cosmic beings. We exist at the intersection of matter and consciousness, where the universe becomes aware of itself and begins to understand its own magnificent complexity. The walking rhythm that has carried us through tonight's journey represents something essential about this cosmic consciousness. It's steady, patient, and persistent, never hurried, but never stopping, always moving toward greater understanding and deeper appreciation of the magnificent universe we inhabit. As our gentle exploration of cosmic walking distances draws toward its peaceful conclusion, we find ourselves transformed by the journey. The universe reveals itself to be both unimaginably vast and intimately connected, both mysteriously complex and elegantly simple in its fundamental operations. The distances we have calculated stretch our minds beyond their normal boundaries, yet they remain comprehensible through the patient mathematics of footsteps and hours. The timescales we have considered dwarf human experience, yet they connect us to the deepest rhythms of cosmic evolution. In contemplating these vast scales, we discover something remarkable about consciousness itself. Our minds, despite being products of a small planet orbiting an ordinary star in an unremarkable galaxy, can encompass concepts that span billions of years and trillions of kilometers. This capacity for cosmic understanding represents one of the most extraordinary achievements in the known universe. The fact that matter organized into the pattern we call human consciousness can contemplate the distances between planets, calculate walking times across geological ages, and find meaning in the vast emptiness of space suggests that consciousness itself plays a fundamental role in cosmic evolution. We are the universe examining itself, measuring its own dimensions, and marveling at its own intricate beauty. This perspective transforms our understanding of what it means to be human. We are not accidental byproducts in an indifferent cosmos, but expressions of the universe's inherent tendency toward complexity, consciousness, and understanding. Our ability to imagine walking to distant worlds represents the cosmos developing the capacity to explore and appreciate its own magnificent architecture. The gentle rhythm of our cosmic walk continues even now, as our consciousness moves through concepts of space and time, exploring the boundaries of understanding and pushing always toward greater knowledge and deeper appreciation. Each thought we form about planetary distances, each calculation we make about walking times, each moment of wonder we experience while contemplating cosmic scales, extends this eternal journey of consciousness through the infinite mystery of existence. The planets continue their ancient orbits according to mathematical laws that will persist long after our individual moments of awareness have passed. Yet, in contemplating these eternal patterns, we touch something timeless within ourselves, some essential quality of consciousness that transcends the temporary nature of biological existence. The cosmic walking journey we have shared tonight becomes a metaphor for this larger journey of consciousness through space and time. Each step represents not just distance traveled, but understanding gained, not just time passing, but awareness expanding, not just movement through space, but evolution toward greater complexity and deeper wisdom. As you prepare for sleep tonight, let the gentle rhythm of cosmic footsteps carry you toward rest. In your dreams, perhaps you will find yourself walking slowly through star-filled darkness, moving at your own peaceful pace toward worlds beyond imagination. Each step in those dreams will carry you deeper into the understanding that you are part of something magnificent and eternal. The cosmos is patient, operating according to timescales that make even our longest imagined journeys seem brief. There is time enough for all the exploration we can imagine, all the understanding we can develop, all the wonder we can experience. Rest well, knowing that you are a conscious expression of the universe itself, temporarily assembled from ancient starlight and cosmic dust, participating in the grandest adventure of all, the evolution of matter into mind, of chaos into consciousness, of simple existence into the capacity for infinite wonder and understanding. The distances between worlds will remain constant for millions of years to come. The planets will continue their patient orbits. The stars will pursue their courses through the galaxy, and the universe will expand into whatever future awaits. And somewhere in that vast cosmic story, consciousness continues its eternal journey, step by step, thought by thought, dream by dream, always moving toward greater understanding of the magnificent mystery we call existence. Sleep peacefully, fellow cosmic travelers, knowing that every breath you take, every heartbeat, every moment of awareness connects you to the deepest rhythms of the universe itself. You are not separate from the cosmos, but integral to its ongoing development, a walking meditation in flesh and blood, carrying the universe's capacity for wonder and understanding wherever your own gentle journey may lead. The quiet mathematics of space reveal something profound about the nature of existence itself. As we drift deeper into our cosmic meditation, we begin to understand that the distances we've calculated tonight represent more than mere numbers. They illuminate the fundamental structure of reality, where space and time interweave to create the vast theatre in which all cosmic dramas unfold. Consider for a moment the profound silence that would accompany our imaginary walker through the void between worlds. Space carries no sound, because sound requires matter to travel through, molecules that can vibrate and carry acoustic waves from one place to another. In the near-perfect vacuum between planets, there are so few particles per cubic meter that sound simply cannot exist. Our cosmic traveler would move through absolute silence, broken only by the gentle rhythm of their own heartbeat, and breathing within whatever miraculous life support system makes this journey conceivable. This silence isn't merely the absence of noise we might experience in a quiet room. It's the complete absence of the very medium through which sound propagates. Yet this silence carries its own profound beauty. Without the constant whisper of wind, the distant hum of machinery, or the subtle sounds of life that surround us on Earth, our walker would experience a kind of sensory purity unknown to earthbound existence. Every sensation would be heightened, every moment of awareness intensified by the vast quietude that envelops all of interplanetary space. The temperature environment our cosmic pilgrim would encounter varies dramatically depending on their distance from the sun and their orientation relative to our star's warming rays. Without an atmosphere to moderate these extremes, surfaces in space experience temperature swings that challenge human comprehension. Near Earth's orbital distance, a surface facing the sun directly would reach temperatures around 120 degrees Celsius, hot enough to boil water instantly. yet turn away from our star's light, and that same surface would cool rapidly to minus 170 degrees Celsius, cold enough to freeze the carbon dioxide we exhale with every breath. This temperature range of nearly 300 degrees represents one of the most extreme environments imaginable. On Earth, our atmosphere acts like a vast thermal blanket, moderating temperature differences and creating the gentle climate zones that make life possible. But in space, without this protective envelope, temperature becomes a function of direct exposure to solar radiation. As our walker ventures toward the outer planets, the sun's warming influence diminishes with mathematical precision. At Jupiter's distance, even surfaces facing our star directly struggle to reach temperatures above minus 100 degrees Celsius. The inverse square law of radiation ensures that each doubling of distance from the sun results in only 1/4 the energy received per square meter. At Neptune's remote orbital position, our sun appears as little more than a very bright star, providing only 1/10,000th of the energy that bathes our Earth. High noon on Neptune feels like the deepest twilight on our world, a realm of perpetual dusk where the familiar warmth of sunlight becomes nothing more than a distant memory. The space between planets also carries invisible rivers of charged particles streaming outward from our sun at speeds of several hundred kilometers per second. This solar wind, as astronomers call it, represents a constant flow of matter ejected from the sun's upper atmosphere, carrying the story of stellar fusion across the entire solar system. Our cosmic walker would move through this invisible current like a boat traveling upstream in a river too tenuous to feel. The solar wind consists primarily of protons and electrons, the component particles of hydrogen atoms stripped apart by the sun's intense heat. These particles carry enormous energy, yet they're spread so thinly through space that their direct physical effect would be imperceptible. Over the vast timescales of our planetary journeys, however, this gentle particle bombardment would accumulate into measurable effects. The constant stream of charged particles would gradually alter the chemistry of any exposed materials, slowly changing their properties through processes that operate too slowly to notice in human timescales, but become significant across the millennia required for interplanetary walking. The radiation environment of space extends far beyond the solar wind to include cosmic rays, high-energy particles accelerated by supernova explosions, and other violent stellar events occurring throughout our galaxy. These cosmic messengers streak through our solar system at nearly the speed of light, carrying information about stellar deaths and births from regions of space we can barely observe with our most powerful telescopes. Each cosmic ray particle that impacts our theoretical spacewalker tells a story about galactic evolution, stellar nucleosynthesis, and the violent beauty of distant cosmic events. Over the 100,000-year journey to Neptune, our traveler would experience roughly 10 billion such impacts, each one a whisper from the deep universe about processes occurring on scales that dwarf even our expanded understanding of cosmic distance. The magnetic environment of interplanetary space adds another layer of invisible complexity to our journey. Each planet with a substantial magnetic field creates a vast bubble in space where charged particles from the solar wind become trapped and accelerated to enormous energies. These magnetospheres extend far beyond the visible boundaries of the planets themselves, creating invisible territories that would influence our walker's experience long before the destination world becomes visible. Jupiter's magnetosphere stretches across a region larger than the Sun, creating radiation belts so intense they would be lethal to unprotected human life within minutes. Our approaching walker would spend months traveling through this magnetic domain, experiencing an environment more hostile than anything found naturally on Earth's surface. The interaction between Jupiter's magnetic field and its largest moons creates some of the most extreme conditions in our solar system. Io, orbiting deep within the radiation belts, experiences particle bombardment so intense that it strips atmospheric particles away and creates auroras visible even from Earth-based telescopes. Saturn's magnetosphere while smaller than Jupiter's, encompasses the planet's magnificent ring system and creates complex interactions between charged particles and ring material. Some of Saturn's moons orbit within this magnetic bubble, while others venture beyond its protective influence into the unfiltered solar wind. The ice giants, Uranus and Neptune, possess magnetic fields tilted at extreme angles relative to their rotational axes, creating magnetospheres that tumble through space like cosmic corkscrews. These unusual magnetic geometries generate complex patterns of particle acceleration and radiation emission, unlike anything found in the inner solar system. As our cosmic walker moves through these magnetic environments, they would experience invisible weather patterns operating on planetary scales. Magnetic storms triggered by variations in solar activity would create temporary intensifications in radiation levels. Particles accelerated within magnetospheres would create aurora displays visible across vast regions of space. The gravitational environment of our journey adds yet another dimension of complexity to the experience of interplanetary walking. Each planet's gravitational field extends far beyond its visible surface, creating invisible valleys and hills in the fabric of space-time itself. The concept of gravitational influence zones helps us understand how planetary gravity shapes the motion of everything in its vicinity. Jupiter's gravitational sphere of influence extends more than 50 million kilometers from the planet, a region larger than the orbit of Mercury around the Sun. Our walker would feel Jupiter's gravitational pull, while still farther from the giant planet than Earth is from our star. This gravitational influence would create subtle but noticeable effects over the final years of approach to each planet. Steps that required the same effort throughout the journey would gradually become easier as planetary gravity began to accelerate our traveller forward. The sensation would be incredibly gradual, perhaps imperceptible from day to day, but unmistakable over months and years of approach. The mathematics of orbital mechanics ensure that these gravitational effects follow precise patterns that remain constant across cosmic time. The same equations that describe the fall of an apple also govern the orbits of planets, the trajectories of comets, and the paths of spacecraft exploring the outer solar system. This mathematical constancy provides a kind of cosmic reliability that transcends the temporary nature of individual lives and civilizations. Gravity operates today exactly as it did billions of years ago and will continue to operate billions of years in the future. The fundamental forces that govern planetary motion represent some of the most permanent features of our universe. Our walking meditation through these gravitational fields reveals the profound interconnectedness of all matter in the cosmos. Every step our imaginary traveller takes occurs within a web of gravitational influences that extends throughout the solar system and beyond. The Sun's gravity dominates the large-scale architecture, but each planet contributes its own subtle modifications to the local gravitational environment. The concept of tidal forces adds another layer of subtlety to gravitational interactions. Just as our moon raises tides in Earth's oceans through differential gravitational pull, each planet we approach would create increasingly noticeable tidal effects on our cosmic walker. These forces would be imperceptible at first, but would gradually intensify as the destination world grows larger and closer. The orbital resonances that characterize planetary motion create patterns of gravitational influence that repeat with mathematical precision across millions of years. Jupiter and Saturn, for example, complete nearly 5 and 2 orbits respectively for every single orbit of the other, creating a gravitational harmony that has persisted since the formation of our solar system. These resonances help explain the long-term stability of planetary orbits, despite the complex gravitational interactions between multiple massive bodies. The same mathematical relationships that create musical harmony also govern the celestial mechanics that keep planets in stable orbits across billions of years. Our gentle journey through the cosmos draws to its peaceful close, having carried us across distances that transform our understanding of space, time, and our own small place within the infinite. We have walked in our imagination for over 100,000 years, covering more than 4 billion kilometers, moving step by patient step from our familiar Earth to the distant blue shores of Neptune. In these calculations, we discover something profound about the nature of existence itself. The universe operates on scales so vast that our entire species represents barely a whisper in cosmic time. Yet our minds can comprehend these immensities with remarkable grace. Through the simple rhythm of footsteps, we have made the infinite feel somehow manageable, the incomprehensible strangely intimate. The walking journey we have shared connects us to the deepest truth about our cosmic home. We are not separate from the universe, but woven into its very fabric, temporary arrangements of ancient starlight temporarily aware of their own magnificent origins. Every atom in our bodies was forged in stellar hearts billions of years ago, making us literal children of the cosmos, walking meditations of matter that has learned to contemplate itself. As you drift towards sleep tonight, carry with you this gentle understanding. Though the distances between worlds stretch beyond human comprehension, consciousness itself represents the universe's most remarkable achievement. In imagining these impossible journeys, we participate in the cosmos examining itself, measuring its own vastness, and finding beauty in its patient, eternal rhythms. Rest well, fellow travelers, knowing you are part of something magnificent and timeless, connected to everything that was, everything that is, and everything that ever will be.